Okay, so let me see. We've been talking about regressions and starting from the linear regressions, and let me see. We cast the problems as a least squares, and you can transform the problems and optimizations. You can do the projections or least square solutions. Either way is fine, or you can use a CBXPy to find out the solutions numerically. And I want to emphasize that the definition of a distance, L1 norms, L2 norms, there are most of the time the outcomes and results are pretty much those are pretty much the similar or pretty much the similars, but there are some pro and cons for each distance definitions. And one of the specific example that I demonstrate or share with you guys that when we have outliers, try L1 norms as well, and probably when you have outliers, probably L1 is give us a little like a better performance. And for we move to the multivariate linear regressions. I mean, I said it's the same as linear regressions and nonlinear regressions. Actually, there is a name for nonlinear regressions, but actually it turns out it's a linear regression for nonlinearly distributed data set. I'm going to say, I'm going to repeat it. There's a name for nonlinear regressions, but actually it's not the nonlinear regression. It's a linear regression with nonlinearly distributed data set, right? And there are two ways that we can look. And so in regression 2, there's some advanced materials and contents that we have to think about it for the regression problems or even for the machine learning problems. And the first thing is overfittings. So when you have your model is too expressive, that means you have a lot of flexibilities, or we have many parameters that can handle the data set in your models. Probably you're gonna have overfitting problems. That's something we don't want to have in general. So we have to redefine, let me see, overfitting problems. And there's some issue with the rich representations. And for nonlinear regressions, another way or perspective or point of view is that linear basis function models. We define some kind of basis functions, and the approximation is going to be linear combination of those basis functions. And I show you the most famous one, polynomials and RBF functions. Those are things that you need to remember. And going back to overfitting problems, in order to avoid overfitting problems, regularizations. Remember regularizations. There are several ways that we can do. We can, for regularizations over here, make as simple as possible. Make your model as simple as possible, or you can add another regularization terms in your objective functions or loss functions. In this example, is that the magnitude of coefficient or unknown decision variables. And in order to over there, we have two ways. One is two norms. That's the most common. And I show that we don't have to stick with two norms. The first norms, there's some advantage on that. So here, let's use one norm, and with only different. And for two norms, it's rich regressions, and one norm we call them LASSO. Remember LASSO, right? So I'm gonna skip in details, and here, using LASSOs, we can do feature selections using the sparsity, right? I think that's where we stopped last time. So let me continue on here. let's think about difference between LASSO and riches. Let me go back to, that's the, let me see, that's kind of, this is the definition of LASSO, like the regularizations. And the only difference for the riches like here is two norms. Remember that's these equations, and let's go back, let's here. And this is LASSO, and this is, here's two norms, like L2 norms. There is L1 norms. And we have two terms in the objective functions here. And we can equivalently, we can transform it like that. So let me show you this one. I want to minimize this one and this one at the same time. And this one, same as the previous one. So we have only like the data feeding terms. And I want to minimize this one as well. That means I'm gonna set the constraint on the magnitude of parameters, use that as a constraint. So what I mean by that is that here we have tuning parameters lambda, something that we have to define it really, and instead of lambdas here we have s of 1. So that's something that the values that we need to define it. And I want to have magnitude of coefficient is less than or equal to s of 1, which that I want to predefine. Within this constraint, I want to minimize that. Does it make sense? Here we can do the same argument, lambdas, and here in a sense of two norms, we can do like that. So here is related to like that. These are related to like. So we can have here in the original optimization problems, it's unconstrained. We have two terms. Now, in order to make comparison between these two, I slightly changed the original optimization problems into like constraint problems. So we have same objective functions, but we have different constraint. The only difference is that the definition of distance or magnitude of vectors. All right, with that, so I want to give you some kind of geometric illustrations to visualize or to understand. So here in theta space, let me explain you this one first. So this means that this is the magnitude, right? So let me show you theta of 1 and theta of 2. For example, if we have two-dimensional space, they can be multiple, but this means that the distance, Euclidean distance. So if we have some set S of 2, that means the same distance. These are the feasible reasons for the candidates of theta of 1 and theta of 2. Over here is one norms, that means right. So in that case, if you draw, then like if those two are positive, then like that. If that's a negative, let me see, like that, you can draw this kind of like these figures. So these are your feasible regime. Now for objective functions, it's defined in two norms. And this is kind of vague and it's kind of difficult to explain it. But if you plot it, and this will be like ellipse. So for these thetas, it's gonna give the same magnitude, and these are the same magnitude. It's like contour, and that means this getting bigger, right? So if we have like that, it's just this is the very small, the theta values are very small, but it doesn't have intersection with the feasible reason. So you have to increase it like that. No solutions and no solutions. If we keep increasing it, this is the first time we do have solutions. We can do same things here, keep increasing it. And now we have, at this moment, we start to have we start to have solutions. But let me show you the difference. Here, that's the optimal solutions that we have. In that case, over there, we have zeros and theta of 2. Right? The optimal solutions, if you make comparison between these two, is that here we know that theta of 1 and theta of those two are very smaller values, but both of them are non-zeros. On the other hand, if you use LASSO or one norms, and most of the in general, many of the solutions goes to zeros. That's kind of why we have sparse solutions out of LASSO. Most of the parameters gonna have zeros. That's why we are able to feature selections. Okay.
Sorry.
This is kind of visual explanations. Any questions?
Yes, I don't understand how to choose S1 and S2.
Oh, you don't know how to, okay, so let me show you, so over there, like before talking about S of 1, S of 2, talking about the lambdas. So this means that now we have two terms, right, in single objective functions. And here the kind of this and how we do for the data fittings, how well we do the data fittings for given data points. And another term is that here is how much we're gonna penalize for the magnitude of coefficient. And lambda is kind of thing that we need to define it. So I want to have penalized a lot. That means I have to increase the value of lambdas. And I want to keep focusing on this one. Probably I have to have a small value of lambda. Here, if you allow to have large value of thetas, probably you're going to increase the S of 1. Or no, I don't want to. I want to keep all the magnitudes as much as as small as possible. That means we're gonna set lambdas like small value for S of 1. S of 1. That's something that we need to define it. So it's kind of, you just give some numbers for the here either lambdas or S of 1 and S of 2s and get the solutions and see if whether it's the values that you like to or not. Then you have, and it's kind of repeating process, iteration process. You have, again, you do to adjust the values. That's why we call it tuning parameters. Okay. So let me move on to, okay, that's how to evaluate it. I think I already mentioned it. Whenever you have data set, you have to split it into training or testing or validation sets and use training data set to build your models. and never show the testing data set to your models, because for testing data set, we already know the answers, but we assume that we don't know the Y values or labels and use that to evaluate whether your model is overfitted or not. So that's kind of like a general strategy or schemes for any kind of the data analytics. So we call it generalization performance. That's all the materials for regression 2. Now I'm going to move on to regression 3 part 3, and this is kind of I think I'm going to show you some of the examples of that. And I mean, if you have this kind of data set, I mean, this is too easy, right? So we use that kind of things a lot during the lectures and either the homework assignment. And the example that I'm going to show you here is that at the first look, it doesn't like seem like this one is related to regression problems, but it turns out you can use the regression problems to solve that. So that's kind of things. Let's see. The first one is that denoising process. Whenever you measured some data set from your sensors, it's reasonable to assume that you have a lot of noise as well, like say X and noise on it. Maybe like, how do I say, this is original and is corrupted. And you're gonna have the data set that you're gonna have is corrupted. And I want to rebuild or reconstruct original or clean by getting rid of the noise out of it. So we call it denoising process. So that will be the first example that I'm going to show you. And it seems like it looks like has nothing to do with the regressions. Let's see. So let me show you what the denoising signal first. We're gonna start with signal represented by vector of X. Suppose we have this nice and clean original signals like that, and it's corrupted. We can write it like that. We add some noise on it. And let me show you. So say that these are the discrete data points that we sampled it, and we going to read, each data points at time instant. Probably gonna read that. So it's X is like I don't know notations. Let me see. Okay, X of 1, X of 2. Again, this is signals in time. We can represent it as a column vector. We can have like 100 data points or 1,000 data points. It's okay. So it's just single column vector. Okay, that's the problems set the definition that we have. Now I want to transform it to an optimization problem. So transform denoising in time into optimization problems. What do you mean by that? That it's reasonable to usually assume that the signal does not change or vary too rapidly, which means that usually like if the data points are adjacent, then we go back to here. If data points are very adjacent, like here, xi, and here xi plus x or I plus 1, these two values, if this time interval is very close to each other, the values are going to pretty much the same, right? Xi in general. If you add noise on it, there might be this, even though these values are very adjacent, there's some rapid change on it. That's the idea. So that's the, I mean, of course, if this is true, the only signal that we have constant, but it's not, right? So it's like smoothing signals though. So that's why I'm saying like approximated. So let's see, how can we denoising process? This is the assumption that we have, and I want to show you that how I changed it into optimization problem. And this is, remember, it's column vector. And this one is original one, and it's corrupted. So let me show. This is original one and corrupted, right? I want to have these two as much as possible. That's why these two, we have two signals. That means we have two column vectors, and as close as possible in two norms. I want to minimize it. That means how much X deviates from corrupted one. I'm going to penalize it. So I want to minimize that. That means I won't have X eventually as much as a corrupted one. I mean, these are unknowns. Okay, so let me ask, if we have this kind of objective functions, what would be the solution of this objective function for X? This is the given, like this one. And if you have this, that means X, the signal that we're trying to find, it's gonna be same as the corrupted one. Right? But that's not what we want. We want to denoising. So another term that we have here, I want to apply this assumption that we made. The adjacent data points, these are rapid changes and squared, and I want to minimize this. And we have tuning parameters, U in that case. Does it make sense? So if mu is zeros, that means if mu is like extremely large, then this one's gonna kick in. Have a lot of impact on it. In that case, so we're gonna have a constant. But in general, we're gonna set tuning parameters U in between. So here, I want X as close as possible to corrupted one. At the same time, I don't want to have rapid changes in X. I want to penalize it. So to make it as smooth as possible, as smooth as possible. So this is optimization problems. So remember, whenever we have optimization problems, we have two general steps. First one is to model it using this kind of mathematical form. The second step is how to find the solutions. Now let's get into the second step. How do you find the solutions? And there's some trick. So this one is like looks familiar. We have two column vectors, and the mix, do the subtractions, we have single columns, we define two norms, we can calculate it, it's okay. But here it's not represented in a column vector, it's represented in each element of column vector, it's a scalar. So let's see, these are the difference between the adjacent data points in signal. So we can say, we can represent it as here. Let me show you. This one's okay. This part is kind of, we need to do some kind of equivalent transformations. So we start from x of 2, x of 1, x of 3, x of 2, x of 4, x of 3, like that, right? This one, say x of 1, x of 2, x of n, we have column vectors, and minus 1 and 1, and rest of them are zeros. Zeros and minus 1 and 1, and rest of them are zeros. Okay, so by repeat that things, we can generalize it like that. Have x columns and another matrix D, like that one, like that. Okay, and when this is like zero vector, so it doesn't matter. And if you think of, if you count it, the k is plus from 1 to n minus 1. So if you think about the dimensions here, we have n, and in over there we have n minus 1 points. So that's the shape of D matrix. And so that's now we are here. This one is kind of, we can use that least square, and this one is also, we can utilize least squares as well, but we have two terms. Now I want to change into this form. Let me show you. So I'm going to show you the answer first, and let's see whether this is it's correct or not. Now so these are A's and this is B. And if you do the math, let me show you. So we're gonna do that way. X sigma u d x and minus x corrupted and zeros. So then x minus x corrupted, and we do squared in mu dx minus zeros, and squared like that. We do summations. So this is same as that one. So I'm gonna go into details, but please at home, please do some calculations or math by yourself to understand the transformations, the equivalent transformations. We're gonna use this kind of trick a lot, either in the homework assignment or exams. So it turns out we can convert it into this kind of form. Now this is same as linear regressions. So we can use many different ways to find out the x. So now it turns out, now we know that these and corrupted gives, or we can program it in Pythons. So in mu we set up 100, and there's some tricks how do you define D matrix and the A matrix as well. and B matrix, B column matrix, and use that so this is the kind of the gray is a corrupted one, and red solid curve is a denoised and kind of the solution that we have. Okay. See how mu affects the smoothing result. And as you can see, if this is 0 means that I'm not gonna penalize the rapid change on. That means the solutions, the optimal solution is gonna same as the X corrupted. Now I'm gonna keep increasing it like that way. And as you can see, more smoothing effect is kicks into the optimization process. Here, mu is affects how much that I'm going to penalize on rapid changes of X. You can use the same implementations using CBX-Pi because it's a linear regression process. So you can use that, the CBX-Pi, things like that. And we can get same or similar, the smoothing effect. Again, in the CBX-Pi, we can see the mu effect. I mean, it's just same as before. All right, so let me summarize this. I mean, show you that the denoising process is not like, I mean, at the first look, again, I said many times that it has nothing to do like the regression problems, but as you can see that it's again, we can use that one as well. And let's here the original problem we had a squared. Now it's removed it. I mean, it's pretty much the same. So in CBX-Pi now had 2 norms. In the original problems that we have some squared. In having that one, we slightly changed it. Of course, the value of gamma might be different. You can see that it's pretty much we do the similar smoothing, denoising or smoothing effect as well. So let's see. Now we have at this point, at this moment, now we get rid of these square terms. Another transformation from here, we can change it again, like that we did it here. We have 2 terms in objective functions. Now we have, without any constraint, now we do have single term in the objective functions. Now we added constraint, but it's equivalent. Like what we did in the LASSO. So of course, gamma and betas, another tuning parameters. So let me show you over there in the CBX-Pi, we can slightly change it. We can do the similar denoising effect as well. So now we are here. Now, why we do these kind of things? Because of this one. Now let's change the original signal. Suppose we have this kind of signals. Now we have instead of smoothing signals like that, now we have like sharp changes like this, like that one. The signal with sharp transitions. Now I add noise on it. So this is the signal that we're going to measure or observe or received or gathered. It's a corrupted one. As you can see, it's a lot of noise on it. The only difference is that the previous one is that the original signal is kind of smooth, but it's not. I mean, most of the data points are smooth, but some discrete data at the time instant, we have sharp changes, like discrete or digital signals like that. And first, I want to apply the same method that we used for smoothing signals before. And this one, we call it total variation problems. You don't need to understand this one at this moment. I'm going to show you, explain it later in a minute. Now, this is what we used it. Quadratic, I mean smoothing, so 2 norms. Now I increase the betas. Do you see any problems? The original corrupted one with the sharp, abrupt changes, we add noise on it. So it's kind of smoothing, which is good. But what's the problem in this case? Somehow, we have smoothing effect here as well. I guess you guys want to have, like, let me change the colors. You want to have smoothings here, but I want to keep the sharp changes because that's not the noise, that's the things that we have in the original signal. In some part, I want to get rid of noise, and at some discrete points, I want to keep that in sharp changer. Any ideas? Let me show you. So remember that I use definition of 2 norms to define the distance or magnitude. Quadratic smoothings smooth out both noise and sharp transitions in signal, but this is not what we want. We want get rid of noise, but I want to keep the sharp transitions in the original or corrupted signals. We are not able to preserve the signal sharp transitions. That's the problem. Any ideas? Any ideas? I'm giving the hint right now. What if I mentioned that many times that there are many different definitions on the magnitude or distance. We don't have to stick with 2 norms. So let's try, any ideas over there? Let's try 1 norm. So for here use 2 norms, and the difference, the adjacent data points, we can use 1 norm. The absolute difference. In a matrix and the column forms, we do like that. Because this one is related to that guy. This one is related to constraint. So now use that problems. Usually this is extremely difficult to solve that, but luckily we do have the CBX-Pi. So I'm gonna use a CBX-Pi to find out the solutions. Let me So you can use a CBX pi. The only thing is that just change, like, remember CBX dot norms and CBX norm, and we do have like, and that's the only thing that you need to change it. And if you change the lambdas, as you can see, we do denoisings and we keep the sharp noise on it. Do you know why? Remember in the regression examples that when you first introduced two norms and the difference between two norms and one norms, when you have outliers, actually this is outliers, correlated, associated with outliers. I want to keep outliers. Okay. I want you guys really take some time to think of this example as well. It's extremely important. So we call it, this is total variations. It preserves the sharp transitions, but this is not bad. And how total variations reconstruct does a better job of preserving the sharp transitions in the why remove the noise. Think about it. Think about it. Okay. Now let's move on to another example that we have. Now instead of just we have time and some kind of the functions or signals in time, we have noise on it, on top of it. You can use two norms or one norms or whatever to denoising it. And let's apply it in image in 2D space. Now I want to apply add one norms to the image, and guess what kind of image that we're going to have. Suppose we have this kind of image on it. Image is nothing but it's in the gray image is like you can consider it image as a two-dimensional matrix, like that. You have, like, we have pixels on it, the same as matrix. So what I want to do is that here, this is the first and seconds. I'm going to convert it into, like, this one. I want to transpose it, and again I want to transpose it, and I want to transpose it in order to make single column. So it's a single column vectors. Then I can apply the same thing that we did for the previous one. Okay. Then if you do that, if you do total variations on the image like this one, you will see this kind of image on it. And again, take some moment, think about why we have this kind of image out of total variations. Think about it, why we have this kind of cartoonish image out of total variations. And hint is that, the hint that I want to remember, this one is same as this guy. Make it flat and keep the sharp transitions, and very flat, and keep the very sharp transitions in these directions. That's how we got this kind of cartoonish image out of this. Okay. That's kind of all the materials that we have for linear, for the regressions. The only thing that you need you guys to remember is that least squared, and for the magnitude you can use two norms or one norms, and kind of remember what kind of different effect that you're going to have out of different definition of distance or magnitude or strength, whatever.